Our topic of discussion is phase diagram. We begin with one-component phase diagram, also referred to as Unary phase diagram. Before we go into the actual phase diagram, let us get familiarized with terms related to phase diagrams. Let us begin by defining the term phase. Phase is a chemically and structurally homogeneous region of the material. Thus, a single-phase material is one that has same composition and structure at every point. Most materials are composed of two or more phases. Example, ice water is a mixture of a solid and a liquid phase. Plain carbon steels are mixture of one phase that is pure iron and second phase that contains significant amount of carbon. The other important term we need to understand before we begin our discussion on phase diagram is the word component. Component can be defined as chemically distinct substance. Phase is formed from component or components. The most common components are 1. Elements can be component. Example, iron, carbon, silicon. 2. Stoichiometric compound can be component. Example, sodium chloride, lithium oxide, silicon nitride. Example of single-component systems include pure elements or molecular compounds such as water, H2O. Example of two-component systems include plain carbon steel, Fe plus C, or seawater, NaCl plus H2O. Common window glass is an example of multi-component system containing sodium oxide, calcium oxide, and silica. Pure aluminum is an example of one-component, one-phase system. In this case, the component is aluminum and the phase is the aluminum with FCC structure. Mixture of BCC and FCC iron is a single-component, iron, two-phase, FCC and BCC, system. Ice water is a single-component, H2O, two-phase, solid and liquid, system. A solid solution of copper and nickel is two-component single-phase system. Similarly, solid solution of nickel oxide and magnesium oxide is a two-component single-phase system. A phase diagram is the graphical representation of the phases present and the ranges in composition, temperature and pressure over which phases are present. We will now begin our discussion on phase diagram of pure substance and see how we arrive at the actual phase diagram. In general, equation for the free energy for each phase can be written using form of equation shown in equation 1. As seen in equation 1, the free energy is a function of temperature, pressure, and composition. For one component system, the free energy equation becomes simplified as seen in equation 2. So for a one-component system, the free energy associated with the phase is a function of temperature and pressure. Thus in these one-component systems, the only important thermodynamic parameters or variables are temperature and pressure. Figure 1 shows the schematic surface in the GTP space generated using the free energy for the phase. Figure 2 is a schematic GTP diagram for a one-component system, showing the portions of the solid, liquid and vapor free energy surfaces which represent lowest free energy conditions. The intersection lines of the free energy surfaces are one-dimensional regions of two-phase stability. Each point of intersectional of three lowest free energy surfaces produces a zero-dimensional region of three-phase stability called a triple point. When these lines and points are projected into a TP plane, the pressure-temperature phase diagram is generated. Figure 3 is the TEP phase diagram derived from GTP diagram. Seen in the figure is the Unary phase diagram of H2O. A vertical line at 1 atmosphere summarizes our common experience with H2O. At 100 degrees Celsius water transforms to steam and at 0 degrees Celsius it becomes ice. The location on the phase diagram where all the three phases of H2O, solid, liquid and gas, coexist is referred to as triple point. Seen here is the Unary phase diagram of iron. It appears that under ambient pressure alpha iron transforms to gamma iron at 910 degrees C and gamma iron transforms to delta iron at 1394 degrees C. Also, at ambient pressure pure iron melts at 1538 degrees C. Unlike the previous phase diagram, in this phase diagram there are three triple points, where three phases coexist. Phase equilibria can be described by Gibbs phase rule. According to Gibbs' phase rule, F equals C minus P plus 2, where C stands for number of components, P is number of phases, and F is the degree of freedom. 2 represents variables, temperature and pressure. When we apply Gibbs' rule at triple point where P equals 3, C equals 1, F becomes equal to 0. So as per Gibbs' rule, none of the variables, pressure or temperature, can be varied to maintain triple point where the 3 phases coexist. Consider a point on solid, liquid line on PT curve of pure water. At any point on solid, liquid line, where P equals 2 and C equals 1, F will turn out to be 1. Thus one parameter can be varied and system with 2 coexisting phases can be maintained. At a point in water, liquid region of the PT curve where P equals 1 and C equals 1, the value of F will be 2. It implies that both the variables can be varied and still a system with 1 phase can be maintained. For most material processing, effective pressure is slight. Therefore, one variable, namely the pressure, can be fixed at 1 atmosphere. In such a case, Gibbs' rule assumes the following form: F equals C minus P plus 1. Allotropy can be induced not only by increasing pressure temperature but also by combinations of both high temperature and high pressures. High temperature and pressure combinations have been able to produce diamond artificially from graphite. The TP range where diamond exists stably is shown below in the carbon phase diagram. As per the diagram, at ambient temperatures and pressures diamond is unstable, though the time necessary for its reversion to graphite under these conditions is sufficiently long, geologic timescale. It may also be seen that heating graphite at atmospheric pressure, in a non-oxidizing atmosphere, simply produces melting, but if the heating is done at sufficiently high pressures, diamond is formed. When the diamond is then cooled to room temperature under pressure and the pressure ultimately released, the artificially produced diamond remains in the metastable condition just like natural diamond.